You open your browser, type www.wikipedia.org into the address bar, and press Enter. Almost instantly, the page appears. We often describe this process using terms like the cloud or cyberspace, words that suggest a weightless, wireless ether where data simply exists. But that concept is a marketing illusion. The internet is a strictly physical grid of millions of miles of fiber optic cables, massive data centers, and heavy hardware humming with electricity. No single government or corporation owns this infrastructure. It is composed of more than 75,000 independent networks that cooperate using shared protocols to move data across the globe. Let's freeze time the exact moment you hit Enter and start a clock in milliseconds. On average, a full web request travels globally and returns to your screen in a window of 50 to 500 milliseconds. That illusion of an instantaneous load screen hides a massive sequence of events. To make that connection, your computer must work its way through the protocol stack, a rigid, sequential layering of software rules that dictate how hardware communicates. Within a fraction of a second, your data has to negotiate passage across thousands of those independently operated networks, known as autonomous systems. To understand the internet, we have to look closely at this frozen moment and deconstruct the exact sequence of logical protocols and physical hardware required to load the single web page. The first problem is translation. Computers cannot navigate using human language like wikipedia.org. They route data mathematically, requiring numerical coordinates known as IP addresses, either a 32-bit IPv4 address or a massive 128-bit IPv6 address. Your browser checks its local memory to see if it already knows Wikipedia's number. When it finds nothing, it sends a query outward to your internet service provider's DNS resolver. This flowchart illustrates the lookup path. Your ISP queries a root DNS server, directing the request down the chain. As shown below, the root points to the top-level domain, which points to the specific authoritative server holding Wikipedia's IP. To ensure this process happens without massive delays, the internet uses anycast routing. There are 13 logical root server clusters, but they operate as hundreds of physical hardware instances placed all over the globe, ensuring low latency no matter where you are searching from. The authoritative server finally returns the target IP address, for example, 208.80.154.224, back to your machine. Domain names are merely a convenience for the human brain. The physical network operates strictly through mathematics, and without this translation layer, navigation stops completely. Now that we have the address, we enter the transport layer. Before your computer asks Wikipedia for its homepage, it must first establish a secure, reliable connection with the remote server. This diagram shows the TCP three-way handshake. Your machine sends a SYN, the server acknowledges with SYN ACK, and you reply with an ACK. The features table explains why TCP is mandatory. It manages flow control, establishes sequence numbers, and guarantees retransmission. Because modern web traffic is encrypted via HTTPS, an immediate secondary negotiation occurs. This flowchart breaks down the TLS handshake. The server presents a digital certificate to verify its identity, and both computers agree on cryptographic keys. This creates a secure, encrypted tunnel through the public internet. Connection always precedes transmission. Security and ordered delivery parameters are locked in mathematically before a single pixel of Wikipedia is allowed to move across the wire. Once connected, the server begins sending the web page, but it does not send the 6-megabyte HTML file as one continuous block of data. Networks have a strict physical limit called the maximum transmission unit, or MTU. Because of this, the file is aggressively sliced into thousands of tiny pieces, usually capped around 1,500 bytes each. Each sliced unit becomes an independent packet, capable of traveling its own route to reach you. This table breaks down the anatomy of a packet. To survive on the open internet, each slice of the file carries strict metadata, a source address, a destination address, a sequence number, and the actual data payload. This architecture, known as packet switching, replaced older circuit-switched networks like landline telephones. Instead of monopolizing a single continuous wire, millions of users can share the exact same physical cables concurrently. Decentralization requires atomization. Slicing files into independent packets prevents network traffic jams and allows data to dynamically route around damaged hardware. At the network layer, these packets hit physical routers. A router's only job is to inspect destination IP addresses and consult massive routing tables to determine the next best physical hop. Because the internet is made of tens of thousands of competing networks, routers use the Border Gateway Protocol, or BGP, to negotiate and share the most efficient traffic routes across corporate borders. Often, these handoffs occur inside internet exchange points, massive, highly secure physical buildings where competing network providers physically plug their cables into one another to reduce transit time and bandwidth costs. When packets need to cross an ocean, they almost never go to space. This comparison table shows why. Satellites suffer from significantly higher latency and lower bandwidth compared to physical glass. Instead, between 95 and 99% of all international internet traffic is carried by 1.5 million kilometers of submarine fiber optic cable, resting directly on the ocean floor. Inside these cables, your electrical packets are converted into pulses of laser light. By using wavelength division multiplexing, a single strand of glass can carry multiple frequencies of light simultaneously, pushing terabits of data per second. This exposes the absolute physical limit of the internet. Light traveling through glass moves at roughly 200,000 kilometers per second, which is about a third slower than light moving through a vacuum. The cloud is a convenient myth that masks millions of miles of ocean floor glass. Ultimately, the laws of physics dictate the absolute floor for how fast global communication can be. Your packets finally arrive at your local router. Because BGP dynamically alters routes based on network congestion, these packets almost always arrive completely out of order. Your browser steps in, reading the TCP sequence numbers attached to each packet to sort the scattered data back into a logical file. If a sequence number is missing because a router on the other side of the world dropped a packet, the system doesn't fail. TCP simply demands a localized retransmission of just that specific missing packet. The TLS encryption is unlocked, and your browser reads the assembled HTML, CSS, and JavaScript, rendering the visual Wikipedia page on your monitor. We stop the timer. This entire process, from DNS lookup to cryptographic handshakes to laser pulses crossing ocean floors and mathematical reassembly, happened in 142 milliseconds. The perfect reliability you experience when loading a web page is entirely synthetic. It emerges directly from software mathematically correcting a chaotic, best-effort physical delivery system. The internet functions through an intense duality. Highly disciplined, strict logical protocols like TCP/IP and DNS, forcibly organizing a sprawling, messy physical infrastructure of routers, cables, and exchange points. More than 75,000 autonomous systems actively maintain this delicate routing balance every second of the day. This global statistics table highlights the true scale. That 142 millisecond sequence we just watched is happening concurrently for over 5.7 billion users, generating more than 400 million terabytes of new data every single day. This 500 millisecond journey represents the most complex, decentralized engineering system ever built, held together by internationally agreed-upon standards of cooperation.